So our next speaker, I'm assuming, is a student of Simon's from Bristol University, and he's going to talk about Oclgrind, which is well, he can tell you about it.
Thank you. Okay, yeah, so I'm from the High Performance Computing Group at the University of Bristol. And we use OpenCL for almost everything we do, as you might expect. So we have all of our applications have at least an OpenCL implementation, maybe with a few others. And we found over the last few years that OpenCL has improved a lot. It's matured, particularly in terms of the support. So we've now got OpenCL 1.2 almost everywhere, which is great. And the drivers and the runtimes have also come along quite a way over the last few years. So we're getting better performance for a bit less effort. And the stability is improving. It's still not perfect, but it's definitely getting there. One of the areas where we still find ourselves wanting more continually is in the tools, though. These have got better as well, and we've just heard some of the vendors have some great tools available. There were a few more yesterday. But we still find ourselves running into some problems where we have code that runs perfectly well on all of our platforms, and then we give it out to someone else, and they say, oh, actually, this doesn't run properly, there's some bugs. So we have those sort of portability issues that we like to be able to debug better. So what I'm going to talk about today is something that will hopefully aim to help fill that gap by providing a platform that can make it easier for other tool developers to create new tools for OpenCL developers. So it's called Oclgrind. So what is it? So basically, it's an OpenCL device simulator. So something that takes your OpenCL kernels and simulates how they would execute on an abstract virtual OpenCL device. So it's unlike other simulators. This is an architecture agnostic simulation. I'll come back to exactly what I mean by that in just a second. And it's built on an interpreter for SPIR 1.2, so the LLVM variant of SPIR. And the way that we aim to achieve or to make it easier for tools developers to build new tools is via a plugin interface, which I'll talk a lot more about in the second half of this talk. And that's how we aim to make it easier to extend Oclgrind to develop tools on top of this simulator. And by supporting SPIR, it's worth mentioning that we can also simulate programs written using other programming models that aren't necessarily using OpenCL C, so things like SYCL we've heard a lot about, C++ AMP as well, and any other programming models or domain-specific languages that can target SPIR. So I mentioned this idea of the architecture-agnostic simulation. I guess we heard yesterday as well about multi-2sim, which is an architecture-specific simulation, so trying to accurately model what's actually going on inside a processor. So in contrast, Oclgrind doesn't model any architecture-specific characteristics. So there's no notion of cache hierarchies, no notion of SIMD execution or out-of-order execution. In the core simulation, it just simulates the abstract description of an OpenCL device that the OpenCL spec provides. So the OpenCL spec has this idea of an execution model and a memory model, and these things describe what kind of guarantees you have in terms of forward progress or lack of forward progress, what kind of synchronization you can perform, and when memory is consistent between different work items or work groups. So Oclgrind just simulates that abstract notion of an OpenCL device. And this is why we find it's useful for debugging portability issues, because we're not simulating a specific device, we're simulating how the OpenCL standard describes an OpenCL device. So just a couple of notes about how you can actually use the simulator as a developer, and then I'll talk about what you can do with it. So as anyone who's written any OpenCL programs will know, there's an OpenCL Runtime API. That's how you control your device, how you initialize things, how you enqueue commands to the device. So Oclgrind has a front end, which is a comprehensive implementation of the OpenCL 1.2 API. So if you have an application that uses the Runtime API, you can just target Oclgrind as another platform, as another device in your system. So you don't have to make any code changes to your application to run it through the simulator. It should just work without any modifications. So that's useful to get things up and running quickly. And as I mentioned, you can provide your OpenCL programs either as OpenCL C source code or as SPIR 1.2 binaries if they're coming from some other programming model. So as well as this runtime API, there's another interface, single kernel interface, So this may be useful if you're in situations where your application has maybe hundreds or thousands of kernels, and you don't necessarily want to simulate every single one of them. The simulation can be quite slow in certain cases. So if you know there's a particular kernel that you're really interested in simulating, you can provide a simple configuration file to describe the launch of that individual kernel, so it only simulates the one kernel that you're interested in. So just as a quick example of what such a configuration file might look like, you don't have to go through this in particular detail, but you simply describe, here's the OpenCL source I've got, the name of the kernel, and how you want to launch it, so the ND range, the workgroup sizes, and then you describe the arguments that you want to pass to the kernel for the simulation, so allocating a few buffers of certain sizes and populating them with some data from ranges or just filling them all with 0. So you can just invoke the single kernel interface with this configuration file, and it will go away and launch the simulation. So just to put the last couple of slides into a picture, because that might make it a bit easier. So this is a high-level description of all the components in Oclgrind. So at the bottom you have the Spear interpreter or OpenCL device simulator, which is the core. You have two interfaces, so the Runtime API, if you've got a straightforward OpenCL application, with OpenCL C kernels, it will go through the Runtime API, or if you've got an OpenCL application with Spear kernels, so SYCL, C++ AMP, that kind of thing. And then you've got the standalone single kernel interface, which can take a single kernel or a single Spear kernel. So where does the plugin interface come into play? It's pretty straightforward. The OpenCL device simulator can provide information to one or more, any number of plugins that wish to see what's going on. So the plugins just sit outside of Oclgrind. They're entirely separate. That means you should be able to develop most of your tools without having to modify the core source of Oclgrind. And that's really what we're aiming for, to make it easier to do this sort of thing. So the plugin interface is what we're using to deliver extensibility. And the idea is that these plugins will register themselves with Oclgrind in order to receive information about what's going on. So this happens via various callback functions. So the simulation will run as normal, and when certain events occur within the simulation, it'll fire these callbacks to any plugins that are registered to it. And it's worth noting as well that these plugins are passive at the moment, at least. So the plugins just observe the simulation. There's no way for them to affect the simulation in any way, to change the execution or memory models. But that might be something we look at in the future. So I mentioned these callbacks. So there's a whole bunch of different things that the plugins might want to know about. Fairly simple things like you want to know maybe when a kernel begins executing or ends executing, when individual work items or work groups finish or begin, when individual instructions, so these will be the Spear instructions or LLVM instructions, when memory is allocated or deallocated in any of the address spaces, so from the host allocating global memory, or local memory being allocated when a work group starts, or private memory, that kind of thing. When memory is accessed, so again, either from the host or device, so when the device, a work item might access memory to load or store a value or perform an atomic operation, or some of the host functions as well to write or read data to and from the device. Those will fire callbacks. And when a workgroup barrier occurs, so you can get some information about when synchronization operations are happening. And all of these callbacks will come with some supplementary information to describe what's going on. So when you're getting a callback about an instruction being executed, you'll receive, what was the operand of the instruction, what were the arguments, what was the result, and the opcode, that kind of thing, and which work item was it, for example. So again, just a quick little example of what a very, very trivial Oclgrind plugin might look like. Again, you don't need to go through this in great detail, but you simply have a base class, the Oclgrind plugin class, which you extend for your own tool. And then in this case, we're interested in the instruction executed callback, so we've overridden that one. And as you can see, it will receive which work item, which instruction, and the result. And in this case, all we're doing with this instruction is printing out the work item ID and dumping out the instruction. So when we attach this plugin to the simulation, what we'll see is we run our application, and this plugin will simply print out all the instructions that are being executed and which work items are executing them. So this obviously isn't a particularly useful example. There's no real reason that you might want to do that, but hopefully you can see how you might extend that to provide some more interesting analysis. So now I'm going to go through a few different examples of plugins that have been implemented using Oclgrind already. So these are all things you can go away and start using today. The first, and probably the most useful, at least for us, is a very simple plugin to check memory accesses. So fairly common issue that we come across in the applications that we develop or that we see other people developing is accessing memory that you shouldn't. So reading or writing past the end of an array or something like that. If you do this in C on a CPU, you'll get a segmentation fault, which is great. It'll tell you that something's gone wrong. On GPU, there's any number of outcomes ranging from nothing happening at all, leading you to think that there's nothing wrong, all the way up to you run your application, it takes down the whole server that's in your office and everyone shouts at you. That does happen. And anything in between. So there's a simple plugin here. As I mentioned, there's callbacks that you can register to find out when the device is trying to access memory, and you get the memory address with that. So you can keep track of how big all your buffers are, and quite simply, whenever a work item tries to access memory, you check the address, is it in bounds or not? And if it's out of bounds, you can produce a nice, easy-to-use error message that can tell you where the problem's actually coming from. I'll show you an example of that error message in a second. You can also check for things like if your buffer's been declared as read-only and you try and write to it. That can cause problems on some platforms. Again, on other platforms, you might not see any issues for a long time, and then one day you'll run it with a different version of a driver on a different device, and suddenly your program will start crashing. And these ones are particularly hard to spot sometimes because these flags are set on the host. So you might spend all your time looking at your kernel trying to find out where's the problem, but actually it's something that host has done wrong by declaring it as read-only when it should be a read-write or something like that. And we've used this to find bugs in real programs, particularly when we run it on programs where we don't think there's any problem. At least the program appears to be working fine. So things like Cloverleaf, which is a mini app in the Mantivo benchmark suite, as far as we could tell, it was running fine. We ran it through Oclgrind. It pointed out a bunch of memory access errors, and I fed that back to the developer, who went, oh yeah, that's actually an issue with our indexing that they hadn't noticed because it was running fine on the platforms that they had tested on, but maybe on other platforms it would have caused an issue. And this is probably one of the most easy Oclgrind plugins that it was to write. There's not a lot to do here. So again, just a good example of how easy it is for a tool developer to leverage the simulator to do something that is genuinely useful. So the kind of error message you get back from this plugin, if it does find an error, is something that shows you we've got a write here of size 4, so we're writing 4 bytes to some memory address that we don't really care about. It tells us which kernel it was, which is useful if you've got lots and lots of kernels running. It tells us which work item, the global ID, the local ID, the group. In this case, we can also see that it's a store instruction, so that's the SPIR or the LLVM instruction. And it shows us the line of source code that caused the problem. So given that we know it's a store, we know it's this write into CI here. And we've got the line of code. We've got the work item that's responsible, so we can go and delve into this in more detail and find out what actually caused this. So that's the first plugin. The second, I guess, is data race detection. So this is another problem that's quite frequent when you're writing OpenCL programs or any sort of parallel programs. And again, is an issue with portability, because you can quite often have programs that work absolutely fine on the devices that you've got, but then you try and run on a different device, which has different guarantees in terms of synchronization and memory consistency, and you find that your program suddenly starts spitting out the wrong answers, and you don't know why. So again, relatively simple plugin to write. This is a naive implementation of data race detection, but we can just keep track of whenever memory locations are read or written, and we store which work item or work group was responsible for that read or write. And then we handle the work group barrier constructs as well, so we can tell when actually there has been some synchronization, so we're aware of that. And then if another work item comes along and tries to read or write from memory that has already been written, for example, we can produce an error message saying, well, actually, there hasn't been appropriate synchronization here, and we can tell the user what's going on. So again, we'll see an error message that looks pretty similar to the last, except this time we're told it's a read-write data race. We're given 2 different entities here, so we've got the first work item with global ID of 2, the second work item with a global ID of 1. We can see actually in this case they're on the same line of code, but this guy's doing a load, this guy's doing a store. And you can kind of see from this example that it's a pretty silly piece of code to write. It looks like we're trying to shift an array one element in place, which is clearly not going to work in parallel. But this gives you pretty much all of the information you'll need to at least get a head start on trying to find out where the problem is. Yeah.
So this depends on how much concurrency you have in your simulator. So for example, if your simulator executes one work item in the area and the next work item in the area, then I might not see the races that happen. So how much concurrency do you have? Some randomized execution where you can do something interesting so to really take advantage of the feature?
Right, so it's definitely true that that it's possible, at the moment at least, to have an application where there is a data race, but Oclgrind wouldn't spot it. The execution isn't randomized, it is deterministic at the moment, although we do parallelize across work groups, so different work groups are simulated in different threads. But yeah, it is possible. There are some limitations with this where there can be data races that aren't observed by the simulator. We find them to be fairly sparse. We haven't found many cases where that actually happens in practice. But again, this is more an example of how you can use this simulator to write a plugin without too much effort. I guess if you spent a bit more time on this, you probably could come up with something that was a bit more robust and did catch some of those cases that the naive approach maybe didn't.
Well, you need to add something to the simulator, right? But it's randomized execution.
Potentially, yes. Yeah, you would need to do that. Yeah, yeah. We've got one or two test cases that, particularly across work groups where we are parallelizing, where they sometimes show up and they sometimes don't. Yeah. And there's one or two other cases as well concerning where you mix atomic operations and non-atomic operations on the same address. There's a few cases there that it can't catch, but that's not something we really see many people doing in practice. If you updated a value with an atomic operation and then tried to read it with a non-atomic operation. Really? OK. Good to know. I'll have to reread the memory model again, I guess. OK. I guess the point is, in that case, the developer might expect things. Yeah. Exactly, right. There's potentially a problem here. Yeah. OK. So then interactive debugging, a little more complex, this plugin. But basically, we can provide something that looks very similar to, say, a GDB-style interactive debugger that allows us to do source line debugging. So we can step through our OpenCL kernels line by line. We can set breakpoints, switch between work items on demand, inspect variables, inspect values in memory, all that sort of thing. And also, it ties in with the other plugins where it automatically breaks when another plugin detects an error. So you can run it with, say, the memcheck enabled. And if the memcheck finds a problem, it will break. And then you can inspect the state of your OpenCL program around the point of that error. So this relies mostly on that instruction executed callback, where we're stepping through instruction by instruction, but skipping over a few if you end up with a source line mapping to multiple instructions. So this case can potentially be used for some functional debugging as well. So if maybe your OpenCL program is running just fine, there's no bugs, but sometimes you get the wrong answers, you could potentially use this to actually print out intermediate values at various points without having to modify your kernels with printfs and all that kind of stuff. So the final example that I'm going to look at in any detail I quite like because it's one that wasn't implemented by me. So this is done by our friends at CoPlay to do with SYCL, which we've already heard quite a lot about. So what these guys did was to take Oclgrind and use it to gather some information about memory accesses within a SYCL program. So logging when work items were reading and writing to memory and that sort of thing. And then after the simulation had completed, they took all this information that they had logged and using a Microsoft Visual Studio plugin, you can then visualize all of that information in a way that can kind of give the developer some insights about the memory access patterns that their SYCL programs have exhibited, and whether or not certain regions of their SYCL buffers are in local memory or global memory, where it might not be so obvious from the pure SYCL code. So this looks something like this in the example that I've got. So there's a few different colors here, and the colors differentiate between when the work items are reading or writing, or between local and global memory. So I think this is, we start off with the global reads for these ones, time across the x-axis, and we have the memory addresses kind of squashed down onto the y-axis so they actually fit in a way that you can actually see. So going across, we can see nice contiguous blocks kind of indicate coalesced accesses, because that's several work items accessing adjacent memory addresses. If you had a strided access, you might see stripes in this. So that would indicate maybe you could try and restructure your data layout to improve memory performance. So this is great. This allows developers to actually see what's going on. And again, implemented by someone else, taking OCLGrind and extending it to do something useful. Yeah. Well, I guess you still see a swizzled access as a contiguous block. No, so this is showing multiple work items accessing. So kind of work items might be all linearly arranged or swizzled. I guess you can click on. I assume you can click on this stuff and see which work item is accessing which bit. I haven't actually played with this myself because this is a CoPlay tool. So please talk to CoPlay more if you have questions about this. There's plenty of them around. Okay, so there's some other features that I'm not going to talk about in too much detail. So you can use this for things like detecting workgroup divergence. So if you don't have every single work item in the workgroup hitting a barrier at the same point, that can be a problem, again, that only occurs on some platforms but not others. If you violate the alignment rules of OpenCLC, you can use it to generate histograms of the instructions that were executed, so you can kind of get a feel for the instruction mix between memory operations and arithmetic operations, and a whole bunch of other things that the list is continuously growing. And actually, some of the guys at Imagination, so another example of when someone else has extended this in the Runtime API, so actually nothing to do with the simulator, but worth mentioning. If you've ever written an OpenCL program, you'll notice that often the Runtime API errors you get back are far from useful. Sometimes API errors map to multiple possible causes, and it's hard to tell what they are, particularly for beginner OpenCL programmers. So there's a little useful flag you can pass to OCLGrind to get the API to print out very verbose error messages for every single error that occurs, giving you a human-readable description of what actually went wrong. So I should also say that all the plugins, with the exception of the SYCL one that I mentioned, all of these plugins are available out of the box with OCLGrind. So if you're just a developer that wants, an OpenCL application developer that wants to use them, you can just download OCLGrind and get going. If you're someone that might be wishing to develop a tool, then you'll have to look at the plugin interface and actually write some of your own code. So finally, I guess I should mention this is an open source project. It's all on GitHub, so you can go away and take a look at the source. There's also binaries available on GitHub, so they work with Linux, Mac, Windows, as you'd hope. And it's also BSD licensed, so nice and permissive. That's why, for example, the guys at CoPlay have been able to take this and actually integrate it into one of their products. And as always, we'd always welcome feedback, contributions in the form of bug reports, pull requests, feature requests, or just let us know whether it's helped you or not. Well, don't let us know if it hasn't helped you, but here we go. So link at the bottom. And I guess we don't have much time for questions, but I'll end there.
Well, let's thank our speaker.
Two very quick questions. First of all, does it show up as a platform and a device in the runtime? And the second question, how flexible would it be to add vendor extensions to this environment?
Okay, so the first question, yes, it does. So you can install it as an ICD, so it will show up alongside your other platforms or on Unix systems. There's just a command you can run that will force it to be the only available platform on your system. The second question about vendor extensions. Good question. I guess, again, if you wanted to extend it in that way, you'd actually have to modify the core source, because at the moment you couldn't do that from the plugin side of things. But I have been thinking about ways to make it so you could write plugins that actually can have some say over what actually goes on inside the simulator. So I think it should be extendable, but you'd have to hack around with the source a bit to do that.
Have you thought about a plugin for doing a unit test framework?
How do you mean? So unit testing your own OpenCL kernels, or?
Yeah, if I have to unit test my OpenCL kernel against, say, host code that's already been tested, I just want to see if my kernels are correct.
So whether they produce the right answers.
Yes.
I mean, I guess you could just run it through the simulator, and because the simulator will produce some results, but the simulator is just another platform, so it's just as likely that, well, yeah. I mean, there's no reason why you couldn't run it through the simulator and see if it gives you the right results, but I'm not sure that's going to buy you anything over just running it on a real OpenCL device. Maybe I'm missing exactly what you're asking there with the unit testing.
All right, never mind.
We could talk about it offline.
Any other questions? Oh, yeah.
What do you do for numerical precision? So are you compliant to conformance tests, or you're more precision than a regular device, or less precision?
I'm not sure how much I'm allowed to say about conformance, but probably more precision because I don't really care about performance so much. I basically just do all the floating point operations as double, and that works, ignoring things like fast relax math. Okay, well, I guess does OpenCL mandate that you can't deliver more precision than it requires? Yeah, because I see your point. Yeah. Good question, but I don't know.
One more.
So you did indicate full support for 1.2. How's 2.0 looking?
Not great. But I'm only a little bit behind what's actually out there at the moment. I guess I've been sitting on OpenCL 1.2 long enough that even NVIDIA have caught up. So, but yeah, it's on my list of things to do. Along with, say, SPIR-V support will obviously be something that's going to be useful, but only when developers are really targeting these platforms in earnest. So yes, 2.0 will hopefully be at some point, but probably months. But it's an open source project, so if you want to contribute, by all means,
Good answer.
go ahead.
Okay, let's thank our speaker again. Do we have